Chapter 5 of our textbook introduces covalent bonding. That's a new type of bonding that involves sharing of electrons, and it works exclusively between nonmetals. It also introduces the idea that molecules are not flat pictures on a page, that they're actual three-dimensional entities. And this snowballs towards the end of the chapter to mention that biological molecules, which tend to be rather large, are dominated by their three-dimensional shape, and that one particular molecule will fit into another shaped receptor quite well, and so we have a biological interaction here, whereas if the molecule were a different shape, it couldn't fit. Okay? So there are a couple of things in this chapter that I don't particularly like the way that the text has done. Again, it's trying to do an awful lot of moderately high-level chemistry in a very, very short section. And then it talks about Lewis structures. Now, Lewis structures are a way of us drawing symbolically the elements with dots around them. And if we know how many electrons, those are the dots, that are in a molecule, we can predict its bonding. It has a little section in this chapter on ionic bonding. Well, we're done with ionic bonding. Ionic bonding was between metals and non-metals, between the extreme left and the extreme right of the periodic table. As far as I'm concerned, covalent chemistry is between non-metals. It's dominated by carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. These are the chemicals that are biochemistry. With that said, let's have a look inside the chapter. We already know ionic bonding. Ionic bonding is where you take a metal and the metal undergoes oxidation. It loses electrons to become a cation. And you take a non-metal, which undergoes reduction to make an anion, and then you make that cation and anion balance charges, and you get an interaction there based on electrostatics to make a compound. Far left of the periodic table, far right of the periodic table. Well, there's another type of bonding, and this type of bonding happens exclusively between non-metals. And it's called covalent bonding. And we're going to take a non-metal atom and another non-metal atom and allow them to share electrons. So there's no direct transfer as there was in ionic bonding. There's a sharing, and instead of making a compound, covalent bonding generates molecules. Let's revisit what we know about atoms. Atoms are organized on the periodic table into periods. Those are the horizontal rows. There are 2 atoms in the first period, there are 8 atoms in the second period, and there are 8 atoms in the third period. There are 18 atoms in the fourth. And what this tells us is that electrons, who are responsible for chemistry, are organized into shells. And it's only the outermost shell that performs the chemistry. That outermost shell, the very outside of the atom, is called the valence, and it's only valence electrons that perform chemistry. Now, an atom's valency, its number of valence electrons, is equal to its group number. So we can invent a symbolism, they're going to be called Lewis symbols, that just give us the elemental symbol and then a dot, and each dot represents a valence electron. And if I look at the number of groups in the main block, I'm only dealing with 8 groups, then as I move across the period, the number of dots increases, ultimately getting to 8. So these are Lewis symbols that represent individual atoms. It is a representation of the atom, and then it shows you a dot to represent the electron. After group 4, those electrons start to pair up. So nitrogen has a pair of electrons and then these 3 individual electrons. Oxygen has 2 pairs of electrons and 2 individual electrons. We're going to call the paired electrons, or lone pairs of electrons, or what our book calls non-bonding electrons. The unpaired electrons are what our book calls bonding electrons. And it turns out only the unpaired electrons perform chemistry in terms of making covalent bonds, sharing electrons. So that means everything in group 1 makes 1 bond. Everything in group 2 makes 2 bonds. Everything in group 3 makes 3 bonds. Everything in group 4 makes 4 bonds because it has 4 unpaired electrons. When I get to group 5, the atoms in group 5 have 5 electrons, but they only have 3 unpaired electrons. So nitrogen can only make 3 bonds. Phosphorus, which is also in group 5, can make 3 bonds. Everything in group 6 makes 2 bonds. Everything in group 7 makes 1 bond. And everything in group 8 makes no bonds. Everything in group 8 is inert. It is unreactive. So we're going to take those Lewis symbols and construct them into Lewis structures. A Lewis structure is symbolically atoms stuck together into a molecule by sharing electrons. So here are some rules. A covalent bond is 2 electrons shared between 2 atoms. Remember that definition, it's very important. Covalent bond is 2 electrons shared between 2 atoms. We're only going to be using the unpaired valence electrons in our atoms, which means what I just said, everything in group 1 makes 1 bond, 2 bonds from group 2, 3 bonds from group 3, 4 bonds from group 4, 3 bonds from group 5, 2 bonds from group 6, 1 bond from group 7, and no bonds at all from group 8. 8 is going to be a very stable number of electrons, and we're going to want that to be a number that we come back to. So atoms are going to combine together until every atom in the new molecule has 8 valence electrons. It has this noble gas core type electron structure. There's an asterisk that goes with that, and that is that hydrogen, because hydrogen is in period number 1 and there are only 2 atoms in period number 1, hydrogen only needs 2 electrons to be full. Now, if you add atoms together and you have bonded all of those atoms together into your molecule, but not all of the atoms currently have 8 valence electrons, you need to make some more bonds. This is going to introduce us to the possibility of multiple bonds. Sometimes it's possible to put 2 bonds between a set of atoms. And remember, all a bond is 2 electrons shared between 2 atoms. So if I shared 4 electrons between 2 atoms, that would be a double bond. And then this one's less of a rule, but more of a suggestion. If atoms appear multiple times in a chemical formula, they're probably on the outside of the structure. Atoms that appear just a single time in the chemical structure, they're likely to appear in the center. Let's look at some simple Lewis structures then. Hydrogen gas. Hydrogen exists as a diatomic molecule, a homonuclear diatomic molecule at that. That means that a molecule of hydrogen contains two atoms, diatomic, and they're both of the same type of atom, homonuclear. Hydrogen only has one electron, and this hydrogen atom only has one electron. And our definition of a covalent bond was two electrons shared between two atoms. So if I share those electrons equally between these two atoms, then this atom on the left is experiencing two electrons, and this atom on the right is also experiencing two electrons. I've made a covalent bond. I've generated a new molecule. Remember, new molecules are from covalent chemistry, which is from nonmetals. Here's chlorine. Chlorine has 7 valence electrons, 7 electrons on the outside of its atom, but 6 of those electrons are from non-bonding pairs of electrons. Only 1 unpaired electron. So 2 chlorine atoms will combine, they'll share those unpaired electrons, and now this chlorine atom on the left is experiencing 8 valence electrons. It has satisfied something that we call the octet rule. We said that combine atoms until you have 8 valence electrons. That's known as the octet rule. The atom on the right also satisfies the octet rule. Here is oxygen. Oxygen is in group 6, meaning it has 6 valence electrons. Electrons start pairing up in group 5. So when I look at an oxygen, I see 2 lone pairs of electrons and 2 bonding electrons. These 2 oxygens will combine. I've made a covalent bond right here, 2 electrons shared between 2 atoms. And when I count the number of electrons on this atom on the left, that's only 7 electrons. So I've not satisfied the rule. This one on the right also only has 7 electrons. 1, 2, 3, 4, 5, 6, 7. So I need another bond. If I take these 2 electrons and combine those, I just made a double bond between those 2 oxygens. That there are now 4 electrons shared between 2 atoms. This is a double bond, and it's one of the reasons why oxygen, 21% of the atmosphere, is so stable. So you'll remember from ionic bonding that metals, things on the left-hand side of the periodic table, tend to give their electrons away, whereas non-metals tend to pull electrons towards themselves. So, if I'm combining 2 non-metals in a covalent molecule, there's a good chance that those 2 atoms don't have the same electronegativity. Electronegativity is the ability of an atom to pull electrons towards itself within a covalent bond. And electronegativity is going to increase as you move from the left to the right on the periodic table, becoming more of a non-metal. And it increases from the bottom, where the atoms are large, to the top of the periodic table, where the atoms are smaller. Let's look at a simple molecule. Here is HF. And this molecule is actually covalent in the gas phase. 2 electrons shared between 2 atoms right here. And I think you can see that all the electron density is on the fluorine end of this molecule. So the fluorine is pulling electrons that it's sharing away from the hydrogen towards the fluorine itself. This makes this bond polar. Now, having a polar bond inside a molecule drastically changes the molecule's position in the world, because oil and water don't mix. Oil is a non-polar molecule, water is a polar molecule, and like dissolves like. So polar molecules like to stick to each other, and non-polar molecules don't want anything to do with polar molecules. So by putting a polar bond into our molecule, does that mean that all molecules with polar bonds are themselves polar? Well, no. We have to learn something about three-dimensional structure before we can make that assumption. And that's what we'll do next. So here are a couple of small molecules, and each of these molecules has an electronegative atom in there, at least one, and so there's the potential for polar bonds. Let's go see what that polar bond does to the molecule in its entirety. First molecule is carbon dioxide. I have a carbon in the center with 4 electrons, and then 2 oxygens around it, each bringing 6 electrons. You have a carbon with a double bond to the left and a double bond to the right. So the carbon makes 4 bonds, has 8 valence electrons. The oxygen makes 2 bonds. This was what we predicted earlier. Oxygen is electronegative, and so is pulling electrons away from that central carbon. But the oxygen on the other side is pulling equal and opposite to it. So carbon dioxide, although it has 2 polar bonds, those polarities cancel each other out, and that molecule is non-polar. If I look at chloroform, here again I have a central carbon, I have a hydrogen, which we would not consider to be electronegative, and then 3 chlorines, which are highly electronegative, pulling electrons away. So from whichever angle you view this from, the hydrogen is on the losing end here, and electrons are being pulled away from it. What we're missing, though, is this is a 2-dimensional representation of what is in reality a 3-dimensional structure. So there's a little bit more that we have to learn about this, but I think at this point we can safely predict that that molecule is polar. It has what we would call a net dipole. And when I look at water, water has an oxygen in the middle. Oxygen brought 6 electrons to the molecule. It has shared 2, 1 apiece from each of these hydrogens, and is pulling electrons away from the hydrogens. And in this sketch, it would appear that that molecule is not polar. And we know that to be patently untrue. Water is a very, very polar molecule. And the reason is water is not a linear molecule. By writing this out in 2 dimensions, we have failed to recognize something important about this molecule's structure, something that is still unrevealed to us. Water is, in fact, bent in geometry, and that means that these 2 forces result in a net dipole that passes through the molecule at a diagonal. Water is indeed polar. So there's something about 3 dimensions that we cannot grasp by looking at a 2-dimensional structure. And that is something that is going to need to be explained to us in an expansion of theory that we haven't seen yet. The three-dimensional part of the puzzle is revealed to us through VSEPR, that is valence shell electron pair repulsion theory. And what VSEPR tells us is that the electrons within a chemical bond and the electrons that are in non-bonding pairs of electrons, the lone pairs of electrons, they repel each other. Electrons have a negative charge, and two negative charges are going to repel each other. So our molecules are going to orient themselves in three dimensions in such a way that they minimize these repulsions. They're going to put the bonds and the non-bonding pairs of electrons as far apart from each other as they can possibly go. And if you watch the full length lecture videos, or you can do this at home, if you blow balloons up, just the regular oval shaped balloons, blow them all up so they'd be the same size, then that acts as a domain. You can't put another balloon inside that balloon. That's a repulsive space. And if you tie balloons together, they just naturally occupy the shapes of the geometries of the molecules that we're about to explain to you. So let's look at what VSEPR theory predicts. If I have a central atom, A, with two bonded atoms, B2, around it, like I would see in beryllium hydride, I would expect that molecule to be linear, because I would be putting the areas of repulsion 180 degrees apart from each other. That's as far apart as they can go. If I put three bonds around a central atom, like I might see in boron trifluoride, then my angle between those bonds would be 120 degrees. This would give me something that is trigonal planar. Now, in class, we would do this with plastic models that are perfect for the bond angle, or balloons, which would also work because we're under quarantine. I've kind of made this up, but that molecule is flat. It is a central atom with three other atoms around it, and this gives me the least amount of repulsion. That is a trigonal planar molecule. Planar meaning flat, trigonal meaning triangular based. When I get to carbon in group 4, something very, very important happens. I can make 4 single bonds. That gives me something that is tetrahedral. When we write a central carbon with 4 atoms around it on paper, we put those atoms at 90 degrees to each other because we're representing it as being flat. But in reality, my molecule is tetrahedral. It has a 3-dimensional shape, and this angle is the same as that angle, is the same as that angle, and I don't know if I'll destroy this by doing it. It kind of has succumbed to its own weight. Those angles are all supposed to be the same. And that angle is 109.4. Now, this is not something new. The tetrahedron is a mathematical construct that is 4 opposite corners of a cube. If you went and you picked opposite corners on the top and then different opposite corners on the bottom of a cube, and then you put something in the center, you would have a tetrahedron. When I get to 5 bonds around a central atom, I make a trigonal bipyramid, where I make a 120 degree angle from the atoms in the equator, and then 90 degrees to the axis. If I put 6 atoms around a central atom, I get something called octahedral, which has all of my angles at 90 degrees. The hedron in octahedron and tetrahedron means faces. So if you cut this out of cardboard, you would have an 8-faced object, and you would have a 4-faced object. It's not about the vertices, it's not about the points, it's about the faces. This is how they're named. Okay, what we'll do now is I'm going to take some of those bonds away and replace them with lone pairs. Okay, let's look at a tetrahedron a little bit closer and replace some of those bonds with non-bonding pairs of electrons, with lone pairs. So here's my original tetrahedron. 4 bonds around a central atom, like in methane, which is a hydrocarbon, makes me a tetrahedron. Every one of those angles is 109.4 degrees. If I take one of the bonds away and replace it with a lone pair of electrons, which I could do by moving one position to the right on the periodic table, and replace that central carbon with a nitrogen, I make ammonia. And ammonia turns out to be a trigonal pyramid. I've taken this space that used to be a bond, and I've put a lone pair, a non-bonding pair of electrons there. Now, we represent a non-bonding pair of electrons with a pair of dots. Sometimes we put those dots into balloons to show the viewer that it's not just a typo on the page, it's not just a splotch, it's actually something real, and it's occupying space. And when we look at the bond angle between the hydrogens in ammonia, we find out that it is less than 109.4, it's 107 degrees. If I put 2 lone pairs of electrons into my formula, again, by moving one position to the right on the periodic table, I make water. And this is where we realize that with a 3-dimensional model, there's absolutely no way that water could be linear. Previously, when we'd written H2O out in 2 dimensions on a flat piece of paper, you think, here's a hydrogen, there's an oxygen, put the other bond as far apart from it as possible. Well, that's ignoring 3 dimensions. In 3 dimensions, we find that this angle is 104.5. And that tells us something fairly important. It tells us that although these electrons in the lone pairs of electrons, the non-bonding pairs of electrons, although they're not doing anything, they are repelling each other more. You get more repulsion from non-bonding pairs of electrons than you do from bonding pairs of electrons. And so, although these are not actively holding the molecule together, they are influencing its shape. And water has a bent shape, which allows it to be polar. Okay, now I'm going to start with an octahedron, and I'm going to replace bonds with non-bonding pairs of electrons. So AB6, I have a central atom with 6 bonds around it. It gets octahedral geometry where all of those angles are 90 degrees. One thing that we haven't pointed out, if the illustration shows you a wedge, that means that the bond is coming out towards you. It's coming towards the plane of the viewer. If it is a hatched line, that's not a dash, it's a hatch, that means that it is going away from the viewer. And if it's just a straight line, then it means that that covalent bond is in the plane of the paper. If I replace one of those bonds with a lone pair, I make a square pyramid. And these angles now are a little bit distorted from 90 degrees. They're a little bit under, but they're approximately 90.
if I replace two lone pairs for bonds, then the lone pairs, because they repel each other more than anything else in the molecule, are going to decide to be as far apart from each other as they possibly can. And I make a square planar molecule, and I get 90-degree angles for everything.